Assalamu alaikum. Hello everyone. I'm Abden Sofiane from Tahrir Mohammed University of Bishar, Algeria, and I will be present our research paper. Let me begin by the topic, which is ensemble learning weighted average meta-classifier for palm disease identification. We move to the next slide. Firstly, we'll begin by the introduction and some previous work. We'll continue by materials and methods. Then we will discuss the results and analysis. And finally, the conclusion and future work. Future requirements pose significant challenges such as famine, sustainability, and climate change, demographic growth. With the global population expected to reach 9 billion soon, according to the FAO, agricultural production needs to increase by 70% to meet food demands. Technology, including IoT, AI, plays a crucial role in addressing challenges, ensuring system sustainability, and offering innovative solutions for future needs, emphasizing collaboration between technology and agriculture for food security. Date palm, a crucial crop in Saharan regions, has been cultivated for centuries. It holds deep central cultural significance, deeply embedded in local traditional rituals and daily life. Algeria ranks fourth globally in date production. This industry not only drives international trade, but also plays a crucial role in creating jobs and supporting both local and national economies. Date palms are highly resilient to harsh desert climate, yet they remain susceptible to disease like brown spot and white scale. This disease can be disastrous, with Bayed alone having killed 3 million palm trees in Algeria over the past century. We move to the next slide. Convolutional methods of detecting palm disease are time-consuming and rely heavily on expert observation and lab tests. This often leads to missed opportunities for early detection, leaving farmers unprepared to prevent the spread of disease. The need for modern approaches is crucial, as AI and machine learning provide faster and more cost-effective solutions. Developing practical tools such as mobile application for disease identification is essential for empowering farmers to quickly detect disease, improving crop health and reducing losses. Many studies have effectively used machine learning and deep learning techniques to classify palm leaf disease and date fruit varieties. This method utilizes advanced algorithms to analyze large datasets. For example, study number 11 classifies stages of white scale disease using SVM and Canon, with SVM accuracy of 98.29% on leaflet images. This study makes several key contributions to palm disease detection by focusing on two specific diseases, white scale and brown spot. It proposed a hybrid CNN-SVM for enhanced accuracy. Additionally, an ensemble learning model was introduced using transfer learning with pre-trained models, ResNet, DenseNet, and Inception. The models were applied to a locally dataset from the Bishar region of Algeria, addressing the lack of data on palm tree disease in this area. Finally, the performance of the ensemble learning model was evaluated and compared to individual transfer learning and CNN-SVM methods. As you can see in this figure, our workflow represents a robust ensemble method with a weighted average meta-classifier, combining three transfer learning models, ResNet, DenseNet, and Inception V3, to identify leaf palm disease. And its performance was compared with CNN-SVM and individual transfer learning models using a local dataset from the Béchar region in Algeria. To perform the necessary experiment, the study was implemented through Python scripts and executed on Google Colab, leveraging its access to GPUs and TPUs. The dataset was uploaded to Google Drive and imported into the Colab environment. The algorithms were developed using several libraries, such as scikit-learn, Seaborn, NumPy, Pandas, and Matplotlib. Google Colab was selected for its effectiveness and ease of use, offering a speedy platform for the deep learning model training and analysis. The presented model utilizes a public dataset from Kaggle, containing over 2,000 labeled dates palm leaf across three classes. To improve image-based identification during the training and validation phases, additional images were locally captured and combined with the public dataset, enhancing both dataset size and evaluation credibility. This resulted in a total of 430 samples for testing the models. Some sample images from the public dataset for healthy leaf and white scale disease are shown in the figure 2A and figure 2B. Figure 2C shows sample images of brown spot disease from the public dataset. And finally, the figure 2D illustrates another sample of brown spot from our local dataset. And now we move on to briefly present the methods used. This study combines CNN for feature extraction with SVM for final classification, replacing the softmax layer to improve accuracy. Images are resized, normalized for faster conversions, and proceed with a batch size of 32. The squad hang loss function is used for multi-class classification. Transfer learning used pre-trained models, Inception, V3, ResNet, and DenseNet to tackle new but related tasks such as plant disease classification. This approach is reduced training time and error by averaging learned future. In this study, the models were trained for 3 epochs using continuous settings, with a dense layer of 412 units, ReLU activation, and 0.3 dropout rate, while freezing the initial 10 layers to retain pre-trained knowledge. Inception V3 is a deep CNN architecture that won the ImageNet challenges. It processes images with input size and feature advanced innovation like fully connected layers, path normalization, and improved convolution layers, enhancing accuracy. ResNet is a deep learning architecture widely used for image classification. It features skip connection or shortcut paths that help address vanishing gradients and network degradation, comprising 50 layers and residual blocks. ResNet improves prediction accuracy by leveraging residual functions. DenseNet 201 is a deep learning model designed to address the vanishing gradient issue. featuring 201 layers that enhance its complexity compared to earlier versions. It consists of dense blocks with tightly connected layers, where each layer receives input from all preceding layers. And now we will discuss the most important method in our study, which is ensemble learning. So ensemble learning integrates multiple models to enhance prediction accuracy by correcting individuals' model error. Our approach combines transfer learning of ResNet, inception, and DenseNet through a weighted average meta-classifier, with base models trained in a public Palm dataset. Weights are allocated according to the performance of each model, and the ensemble's effectiveness is evaluated using a local dataset with metrics such as accuracy, precision, and confusion metrics. Now, let's proceed to the results and analysis slide. CNN-SVM classifier yielded a training accuracy of 95.83%. However, when tested on the local dataset, it achieved a testing accuracy of 94%, which was the lowest among all models evaluated. Transfer learning used pre-trained models was also evaluated. Very acceptable training accuracy of 99.86% was yielded by the inception V3 model, and testing accuracy compares 97%. The DenseNet and ResNet showed not bad outcomes, 99.82% and 99.01% and 96 and 97% for training and testing accuracy respectively. The ensemble learning demonstrated the highest performance in this session by employing a weighted average meta-classifier to combine prediction from the previously mentioned transfer learning methods. By assigning weights according to each model performance, ensemble learning achieved an impressive training accuracy of 99.94% and a validation accuracy of 98.14% after 10 epochs, as shown in the figure. Ensemble learning achieved also a testing accuracy of 98%, indicating its robustness in classifying local samples. All ensemble learning prediction results on the test dataset have been illustrated in Figure 4. Finally, I'm going to compare our approach with other studies. As shown in Table 3, our approach not only achieved superior accuracy compared to prior studies, but also effectively addresses the challenges associated with a locally collected dataset. Unlike studies 15, 18, and 20, which primarily rely on public dataset, few studies such as 11 have utilized ensemble learning, and those were also limited to public dataset. The use of weighted average meta-classifier and base pre-trained models distinguishes our approach by leveraging the benefits of multiple models to enhance overall performance and reduce the risk of misclassification. This supports our hypothesis that ensemble learning outperforms individual models, specifically with local datasets. In conclusion, I'd like to summarize the key points we have covered. This study explored three machine learning techniques for classifying palm leaf disease: CNN-SVM, transfer learning, and ensemble learning. The results demonstrate the model's potential to help farmers in prediction and managing palm disease. While CNN-SVM achieved a decent accuracy, transfer learning models reached higher accuracy between 96 and 97%. The ensemble learning model using a weighted average meta-classifier achieved a high accuracy of 98%, showcasing the effectiveness of combining multiple classifiers. This work advanced upon DC's classification using a locally captured dataset, addressing challenges related to limited local data. Future research should refine these models and development effectiveness tools like mobile apps for real-time disease identification and explore their application on other plant diseases and environments. Now, these are the references I used in my research paper. And finally, I would thank you for your attention.